So welcome everyone. Why don't we get started in a few minutes? This is, there are two things going on here. First, there's the award given out in honor of Paul Silver, and that'll be presented over the next few minutes. And then we'll have Rainer Rommel give the Bowie Lecture. And fortunately, we can run out of time in this room because there's nothing going on afterwards. So if we go beyond 6 p.m., that's okay. And I'll remind you that there's a Geodesy reception at 6:30 over in the Marriott. So why don't I turn this over to Peter Shearer, who will present the award in honor of Paul Silver. Oh, I'm sorry. And also Karen Fisher.
Good. Thank you all very much for being here. This year, the Geodesy, Seismology, and Tectonophysics sections are introducing an exciting new award, the Paul G. Silver Award for Outstanding Scientific Service. Starting this year, the award will be given annually to a member of the Seismology, Tectonophysics, or Geodesy sections who has made outstanding contributions as a mentor of junior colleagues, through leadership of community research initiatives, or through other forms of altruistic research collaboration. And we're very happy that Natalie Vallette Silver, Paul's wife, his daughter Karen, and other members of the Silver family are here with us tonight to share in the presentation of this new award. It is very fitting that this new award is named in honor of Paul Silver. Paul was an outstanding example of a top-flight research scientist who gave back very generously to the fields of seismology, geodesy, and tectonophysics. Born in 1948, Paul obtained his undergraduate degree from UCLA and his PhD from the Scripps Institution of Oceanography. In 1982, he began his storied career at the Department of Terrestrial Magnetism at the Carnegie Institution. Paul made a number of pioneering research contributions. His classic papers on shear wave and splitting have inspired literally hundreds of other studies of anisotropy in the Earth's mantle. And his inferences about deformation in the lithosphere and asthenosphere have played a key role in how the community views continental formation and evolution and the dynamics of flow in subduction zones. Paul also made key contributions related to earthquake source properties, particularly deep earthquakes, the processes behind earthquake precursors, and also the interaction of crustal stress changes and earthquake occurrence. But this award in particular honors the generous and creative ways that Paul gave back to the field through his service. He excelled as a mentor to young scientists, many of whom I see in the audience today, and many of them have also become leaders in the field. Paul also played a key role in creating and guiding a number of important community research initiatives. The Plate Boundary Observatory is a recent and shining example. The exciting science now flowing from the geodetic and seismic stations related to the Plate Boundary Observatory and the EarthScope project as a whole are evidence of the significance and creativity of Paul's scientific vision. This new award will be a permanent tribute to Paul's work as a researcher, as a mentor, and as a driving force in the field. And now I'm very happy to turn the podium over to Peter Shearer, who will present the first Paul G. Silver Award for Outstanding Scientific Service.
Okay, so it's my honor to now present the first Paul Silver Award, the 2012 award. It goes to Andrew Nyblade. Andy got his bachelor's degree from Wittenberg University in Ohio. He received his PhD in 1992 from the University of Michigan. He then did a postdoc at Penn State, where he's largely been ever since. Became a full professor in 2007. Andy is a first-rate scientist who has specialized in seismic and other geophysical investigations of the African continent, which have highlighted the unique dynamical and thermal properties of the African mantle. But today we are recognizing his truly exceptional service contributions, in particular his development and leadership of the Africa Array Project, which has established key programs to improve African geophysics, education, and instrumentation. Working in collaboration with African scientists, Africa Array has installed a number of seismic stations across Africa while training young African seismologists in order to build an in-house capability to collect, analyze, and interpret the data, which of course are also freely available to scientists around the world. The goal is not simply to collect African data and leave, but to build local institutions, infrastructure, and expertise. The program is now expanded to include geodesy and other fields. The success of this project required Andy's vision and drive, his ability to build and sustain relationships, and his perseverance in obtaining funding from a variety of sources. He has supervised and mentored many African students who have come to Penn State. In addition, Andy has worked to improve geoscience training for students in the United States, in U.S. Minority serving institutions, including historically black colleges and Hispanic serving universities in Texas and California. He has served as an outstanding research advisor and mentor to numerous younger scientists, many of whom have gone on to faculty positions themselves. Overall, Andy Nyblade has compiled an outstanding record of service, including unique contributions to educating underserved populations in both Africa and the United States, as well as obtaining new data sets and important new research results. He is truly deserving of the Paul Silver Award for Outstanding Scientific Service. Please join me in congratulating Andy Nyblade. Congratulations.
Well, congratulations, Andy. The next item is to welcome, I have the honor of welcoming the 2012 Bowie Lecturer. My name's Dave Sandwell, and Tim Dixon is here with me. He's the incoming Geodesy president. The Bowie Lecture is given each year, sponsored by the Geodesy section of the AGU, and we select an outstanding member of our group to highlight their field of research. The topics rotate among the major fields of geodesy, and this year it's my pleasure to introduce Rainer Rummel as our Bowie Lecturer. Rainer is a professor of geodesy at the Technical University of Munich, and if I went through his complete resume and list of awards, we'd be here all evening and we'd have to go to the reception without a talk. So I'm just going to highlight a few things that Rainer does. His research is really focused in many areas of geodesy, but in particular, much of his research is focused on the development of the Earth's gravity field in terms of spherical harmonics by tracking the trajectories of artificial satellites. Since the early 1980s, geodesists like me and many other old-timers have really dreamed about recovering a high-resolution gravity field and even possibly the time variations in gravity, which seem a little strange. And over the past decade, these dreams have really become a reality with enormous improvements in resolution, accuracy, and also the ability to resolve time dependence. The most recent satellite mission, GOCE, is providing a remarkable new view of our planet, and Rainer is heavily involved in this mission. He's the principal investigator on the high-level processing of the GOCE mission. So I introduce Rainer. The title of his presentation is How Attractive is Our Planet? So I think he's going to try to answer that question. I'm going to switch. Here, it's Reiner. Thank you, Reiner.
Thank you, Dave, for the kind introduction. Thank you, Tim and Dave, for giving me the opportunity to do this lecture today. Dear colleagues, dear friends, in 1929, William Bowie published a paper with the title Tilting of Mean Sea Level. It was published in Galland's Beiträge zur Geophysik, that was at that time one of the leading geophysical journals. Bowie had made the observation that the mean sea level relative to the geoid is tilting northwards along the east coast of the United States as well as along the west coast. He has found this based on continental scale geodetic leveling lines, which were connecting the major tide gauges along the coasts of the United States. In the 70s, there was new measurements, new geodetic evidence, and the whole issue became what I would call a historical controversy between geodesists and oceanographers, because this northward tilt is counterintuitive from an oceanographic point of view, because there one would expect that the sea level is tilting towards the equator due to the warmer water there and thermal expansion. The leader of the geodetic view was Iron Fisher at the time, and of the oceanographic view, William Sturge, and there were many papers on this controversy. Now, we are currently conducting a study for the European Space Agency on height determination, height unification, and heights on tide gauges in the context of the GOCE satellite mission. And in the context of this study, Phil Woodworth and some colleagues revisited this old question. And what you see on this slide is mean sea level along the east coast of the United States at the tide gauges. You see in red the mean sea level at the tide gauges of the United States, expressed in the height datum of the United States. In blue, those of Canada, expressed in the height system of Canada. And still, this northward drift or tilt is present. And Phil compared it with an ocean circulation model, the MIT model, modified in Liverpool at the National Ocean Center there. And we see the southward tilt, which the oceanographers always claimed. They then repeated this experiment by replacing the heights as derived by geodetic leveling by GPS leveling. In other words, by taking the simple difference of an ellipsoidal height derived by GPS and the best possible geoid model, in this case derived from a GRACE GOCE solution, but extended by EGM 2008 in order to model also the small scales. And what we can see is that this difference is practically perfectly gone apart from a really arbitrary offset. The bad thing about this result is that oceanographers were right and we geodesists were wrong. Now this problem is solved, and we can really now connect all tide gauges worldwide roughly with a precision of a few centimeters. What is still to be resolved, in my opinion, is where this strange and excessive northward tilt in geodetic leveling comes from, because it exceeds the formal errors by 1 order of magnitude, and it still needs to be resolved. Similar observations now on this disappearance of these latitude-dependent drifts were made by the Australian colleagues and in New Zealand too. Now I chose for this lecture the title, How Attractive is Our Planet? Not so much to talk about the beauty of our world, even though when you come from Europe and you cross the Rocky Mountains and fly down along the coast of California towards San Francisco, it is just wonderful. It is my understanding that geodesy is a measuring science, and it has essentially 2 main objectives. One of these objectives is the determination of the gravimetric figure of the Earth, of the geopotential surfaces, and in particular of the geopotential surface at mean sea level, the geoid. And this is achieved by measuring the gravitational attraction of the Earth with better and better accuracy. The other main objective is the determination of the physical surface of the Earth, the geometric surface of the Earth, with mountains and valleys, with ice shields, and with the ocean surface. And we can observe that in both of these pillars of geodesy, space age has brought a real revolution, an improvement in accuracy of 2 to 3 orders of magnitude. And the advancements in technology in recent years have even pronounced this trend. When I talk about geometric surface, I refer to GPS or INSAR or ICE or ocean altimetry. And when we talk about the progress in the gravimetric determination of the Earth, I talk about GEMS mission as the first one, and GRACE, the fantastic mission, and GOCE. It is my conjecture, my hypothesis, that the great successes that were achieved in recent years by geodesy for earth sciences came mainly from the joint analysis of these two, from the joint analysis of the geometry part and the gravimetry part. And I tried to exemplify this with 4 examples. Think of the detailed determination of the Moho discontinuity, or in general of the mass imbalance in the solid Earth and the dynamic topography of the solid Earth, from improved topographic models and from gravimetry. Or the fantastic now result on the mass loss in Antarctica derived from GRACE and from ice and radar, from laser and radar altimetry. Or the determination of the ocean topography from altimetry and the best possible geoid model. Or now the possibility to separate for the first time the steric and the mass part of sea level change. Always it is this duality of the geometric and the gravimetric part. I will in my talk mainly focus, of course, on the gravimetric part. We'll mainly talk about the satellite mission GOCE. This was, so to say, the mission order I got from Dave. Satellite gravimetry started, if you are old enough, already with the first 2 satellites, with Sputnik 1 and Sputnik 2. Sputnik 1 was launched in 1957, and already in 1958, 2 papers were published in Nature, one by the Czech scientist Buchar, and the other one by the British King Heel, where they published a greatly improved value of the Earth's oblateness. You could say in one moment, 100 years of classical terrestrial geodetic activity has been made obsolete. Another revolution came with GPS, because now we are in a position to track any low Earth orbiter with high precision, continuously and three-dimensionally. We can derive from this the satellite trajectory with centimeter precision. We can quantify the non-gravitational part of this trajectory by putting an accelerometer into the satellite and derive from these gravimetric orbits a good map of the Earth's gravitational field or of the geoid. This works very well, but it has an intrinsic limitation as expressed by Newton's universal law of gravitation, namely that the attraction, the gravitational attraction, decreases rapidly with the square of the distance from the masses. So whatever we do, we can with this approach only determine a largely smoothed version of the Earth's gravitational field. One way to counteract this damping effect is to use a gravitational gradiometer. And it would be very tempting for me to talk about the whole development of this idea from the early 50s, where there were published the first ideas, via the Williamstown report, and via many trials in the United States and in Europe, till finally a working gradiometer was constructed for the GOCE mission by Honora in Paris. GOCE is the first satellite with a gradiometer. GOCE stands for Gravity and Steady-State Ocean Circulation Explorer. It's a satellite mission that was launched in March 2009. And it has two goals. One is the precise determination of the Earth's gravity with 1 part per million, 1 milligal accuracy, and of the geoid with radially precision of 1 to 2 centimeter. And to do both with a spatial resolution of roughly 100 kilometer, corresponding to a spherical harmonic expansion up to degree and order 200. The orbit of GOCE is circular. The inclination is sun-synchronous, so the angle relative to the equator plane is 76.7 degrees, which means that the two polar gaps are left, unfortunately, without data. And the altitude is spectacular, because the orbit altitude at perigee is only 255 kilometers. The mission is now already in its extension phase, and it will very likely end by the end of next year. Literally, the centerpiece of the mission is the gravitational gradiometer in the center. It is a 3-axis instrument, each axis 50 centimeter long. It is 3 orthogonal one-axis gradiometers, each consisting of 2 ultra-precise accelerometers, and from the acceleration difference, the second derivatives of the gravitational potential are derived, the elements of the gravitational tensor. And the component XX in flight direction, YY, cross to the orbit plane, and ZZ in radial direction are derived with high precision, and in addition the component XZ. The mission, the sensor system, has also a GPS receiver for orbit determination, for the determination of the long wavelength structure of the field. It carries 3 star sensors in order to determine the orientation of the instrument, but also in order to quantify angular accelerations and velocities, which are also measured by the gradiometer. It has 2 ion thrusters in order to keep the spacecraft at this extremely low orbit. and it has no moving parts in order to avoid that not gravitational effects from the spacecraft are measured by the gradiometer. Also, the material that has been chosen is very stiff and thermal control is very high. Now, usually the gravitational field is expressed in a series of spherical harmonics. The triangles shown here with their color code show the contribution of each of these highly precise gradiometer components to a total solution. The triangle has as a vertical axis the degrees starting from 0 up to 220 on the top, and the orders to the right and the left-hand side, CNF and SMS. We see, for example, that the Vxx component is rather strong on the so-called zonal coefficients, so with low order, while YY is complementary, being very strong for the so-called sectorial components. The two together are complementary and would give a rather isotropic picture of the gravity field. The ZZ component is isotropic. And from Laplace equation, we have a wonderful check, namely that these three triangles, XX, YY, and ZZ, have to add to 0. So we have a wonderful check about the real noise level of the gradiometer. We also see the contribution of Xz, which is rather modest. The GPS orbit part gives the very low harmonics, degrees in harmonics. And because the polar gap data are missing, we have to introduce a slight regularization at the poles with a contribution, a total contribution of only 0.2%. Meanwhile, a whole series of spherical harmonic models have been derived from GOCE or from a combination of GOCE and GRACE. They differ in the rationale, how the data are processed, and in the extent. We have so far 3 releases, the data amount that has been used, and they can be downloaded. Last week, I saw the newest release, release 4, which is currently at the validation phase. The fields are typically extending up to degree and order 250 or even 260 now. And the newest release is based on a reprocessing of the data, an improved algorithm of level 1 processing. Now from GOCE, we have now for the first time a rather detailed gravity field of Antarctica, for example. You see on the left-hand side, more or less, the raw measured ZZ component for the ascending arcs. I would have to make a separate map for each of these components and for ascending and descending because of the changing orientation of the instrument. We see also the correlation to typical tectonic features of Antarctica, and on the right-hand side of the gravity field derived from this data. In the middle, we see the polar gap where we don't have data. And several groups around the world are meanwhile working on the geophysical analysis of this data set. Now, of course, we would like to know the quality of the GOCE data, and this is a difficult thing because we think or we hope it is the best gravity field there is. The best way to compare, in our opinion, is to compare with the gravity model EGM 2008, which is derived from GRACE, from 3 years of GRACE and terrestrial data. When we compare the geoid heights in different areas of the world, up to degree and order 200, we see the picture exactly as I would have expected it anyway. We see an excellent agreement in those areas of our planet where we anyway have a very good geodetic infrastructure, like in North America, in Europe, Australia, or in Japan. While we have really large discrepancies, also in areas where we would expect this, in parts of South America, parts of Africa, Himalaya, China, Southeast Asia. And in EGM 2008, in Antarctica, there were no terrestrial data used. They were not available. It's only based on GRACE. So in Antarctica, we see the RMS difference relative to GRACE there. Now, EGM 2008 is, as I said, based on 3 years of GRACE and a fantastic collection of terrestrial gravity material. And this collection, and Steve Kenyon could explain this much better than I could do, has 8 different data sources, and they are here in the color code of this map. Probably the weakest data set of this is the so-called fill-in data in light gray. On the ocean, it is altimetry-derived gravity anomalies, the Danish solution and the one by Vzz and Vxz, I guess. So what we tried to do is now for these 8 data sets to check the difference between GOCE and EGM 2008. And this is a slightly busy and difficult plot. On the left-hand side, we see this comparison. It's done in steps of 10 spherical harmonic degrees, ranging from 20 up to 220. And on the vertical axis, we see the RMS differences. And the blue high line shows the rather bad performance of the fill-in data already starting at degree and order 60. Up to degree and order 60, the 2 solutions almost perfectly agree, and then they start to diverge. In purple, we see the comparisons in Antarctica between GRACE and GOCE. We see that already at degree 60, there is a slight divergence visible, and then it's getting really rough from degree 160 on. Another test was to do the same approach comparing in selected geographical areas. And we see on the right-hand side the dark blue line with the large discrepancies in South America. In light blue, the crosses for China, Africa, Southeast Asia. But what was surprising for me, we see also a rather large discrepancy with the data derived from altimetry in the Antarctic circumpolar current area, where probably altimetry has difficulties due to the high dynamics there and due to the seasonal ice cover. Let me come to the ocean application. One of the main goals of GOCE was to help to derive detailed ocean topography. The basic formula is really simple. We take the mean sea surface as derived from, meanwhile, 20 years radar altimetry, and we subtract the geoid model from GOCE, and the difference is the mean dynamic ocean topography. From the point of view of mathematics, it is a bad thing to do, to take the difference of 2 large quantities in order to arrive at a small quantity. So some caution is necessary. But the main point is this difference is taken from 2 satellite systems of a complete different characteristic. Radar altimetry working profile-wise, and the measurement of a field quantity with GOCE. So one has really to make sure that these 2 systems work in one and the same coordinate system, not even coordinate system, but terrestrial reference system, including all the necessary reductions being the same, like permanent tides in many of those details. If this, and the two data sets have to be made spectrally consistent. Now, once all these precautions have been done, we arrive at really wonderful maps of dynamic ocean topography, as shown here for the North Atlantic and taken from a work from Rory Bingham and his colleagues. What we see here is the topography of the order of 1 meter of the Gulf Stream and the counter current, the laboratory system in blue. This topography is maintained where it is due to the balance of the pressure difference of the topography and the Coriolis force. The water is flowing along the contour lines of this topography on the northern hemisphere in clockwise direction, southern hemisphere counterclockwise direction. The slope of this topography is proportional to the velocity, to the geostrophic velocity. So where the contour lines are narrow, velocity is rather high. Where they are far apart, velocity is small. So it's rather easy to derive geostrophic velocities from it. And here's an example of the Gulf Stream. I think it's a wonderful example, and we can now quantify the geostrophic velocities in magnitude and in direction. And we should realize that this is now for the first time that we can globally, by geodetic means, without ocean data, provide to the oceanographers this topography and velocity maps. We do currently tests how far we can get in terms of spatial details, and even if we take the expansion up to degree in order 210, we see still clear Gulf Stream signal in the data. In Munich, our focus area is the Antarctic circumpolar current, because we do this work in cooperation with the Alfred Wegener Institute, and they focus on this area. The ACC is probably the most dynamic ocean part of this globe, and from climatological point of view also the most interesting, probably also the one least known. We see again the geostrophic velocities, but also included the front systems in black here. We give the Alfred Wegener Institute the grids of the ocean topography, and they assimilate it in their ocean models in order to improve their estimates of mass and heat transport there. I said that a fundamental problem of satellite gravimetry is this attenuation effect, the distance from the masses. And the solution to it is an old principle of physics, not to measure absolute quantities, but differences of quantities in order to emphasize, in this case, the small scale effects. Theoretically, the GOCE gradiometry can be seen as measuring the acceleration differences between, as shown here, 4, or in the case of GOCE 6, free floating test masses inside a satellite orbiting the Earth. One can easily understand that the lower test mass is slightly attracted more than the upper one, and that the front one is attracted in a slightly different direction as the rear one. What GOCE is measuring is these small acceleration differences. And they are really small. They are on the order of 1 millionth of g on the Earth. And in order to make these measurements interesting, you have again to measure this with 6 orders of magnitude, which makes it 10⁻12 meter per second square. So a great achievement to build such accelerometers. This is the principle of GOCE, and it is only a baseline, the difference between these test masses is only 50 centimeters. In the case of GRACE, one could say these test masses are flying on separate spacecraft, 200 kilometers apart. Two satellites following each other in the same orbit, and the distance measured with micrometer accuracy. So in a certain sense, one could interpret this principle as being a one-axis gradiometer with a length of 200 kilometers. And this long arm for a gradiometer has a certain quality. If we combine GRACE and GOCE data in one solution, we get the following result. On the right hand, so this is a contribution analysis. On the right hand side, we see the contribution of GRACE, and we see that up to degree and order 60, it almost contributes 100% to the combined solution. At degree and order 120, it's still 50%, and then GOCE takes over and becomes 100% beyond, above degree and order 140. So the strength of GRACE is this fantastic precision at low degree and orders, that of GOCE of high degrees and orders. We can look at the same question in terms of degree variances, so taking the RMS average per spherical harmonic degree. Then we have on the x-axis the degree of development or the spatial scale on the Earth's surface, and on the vertical line, the power. In black, we see the famous Cowler rule of thumb, the typical degrees with the square of the n of the signal itself. So from low degrees to high degrees by 3 orders of magnitude. And we have also included in this graph the error curve for GOCE and for GRACE. For GOCE, the line would cross the signal line somewhere at degree 200. In reality, it's meanwhile 250. This expresses the high spatial resolution of GOCE. The GRACE spatial solution is less than degree and order 150 probably. But due to this long baseline of 200 kilometers, the accuracy at low degrees and order is extremely high. And this is very important because this is where the temporal variations of the gravity field become measurable. Temporal variations due to mass change in the continental water balance, due to deglaciation, or due to the mass contribution of sea level range. This is what becomes, because of this high precision, measurable with GRACE. If we would try with GRACE results to resolve the geostrophic velocities with very high spatial details, one would simply fail as shown here. The strength of GRACE is, in my opinion, the resolution of the temporal variations. So where are we now in geodesy? The precisions or the accuracies of our geometric and gravimetric methods are meanwhile so high that we even can detect temporal variations, as all of us know. Either we can compare the temporal variations of the geometry relative to the geoid, to the static geoid, or the temporal variations of gravimetry itself. The problem is, of course, that these temporal variations are really small. And if they are related to climate change phenomena, they have to be monitored at least over 3 or more decades. And we have to get them free of systematic distortions. And I just remind us of the agony with radar altimetry, what an effort it took to get radar altimetry free of systematics, and we are still not sure whether we have achieved this goal perfectly. And we have to achieve that this geometric and the gravimetric approach are consistent at the millimeter or sub-millimeter level. And I think this is really not trivial to get them in the same system at such a high accuracy into the same terrestrial reference system. In my opinion, we have therefore to think more and more in terms of a global geodetic observing system. First, in order to get the various satellite methods consistent in one system, but also to establish the link with terrestrial methods. Think of tide gauges, think of seismometers, GPS receivers on the ground. So to me, the answer is to work towards this and support the global geodetic observing system. I organized in 2007, together with a friend, Radboud Koop, a workshop on the future of satellite gravimetry at the Technology Centrum of the European Space Agency in Noordwijk in Holland. This is a slide from the presentation by Mike Watkins. And what it shows is error curves per degree. In light blue on the top line, the GRACE performance, the error curve, the line below the theoretical GRACE performance. In green then, GRACE if it would fly at 200 kilometer altitude. In brown, if GRACE would have a laser ranging system, but again at 450 kilometers, or a laser ranging system at 200 kilometers. So we see that with laser ranging link instead of K-band, one would probably be able to gain another 3, 4, or even 5 orders of magnitude, which would greatly increase the spatial resolution of such a follow-on system. Mike put also in this graph the problem of aliasing due to the imperfect knowledge of ocean tides or atmospheric phenomena. So it is not only a technological problem for a future mission to get improvements, but at the same time, we have to make sure that the modeling of our geophysical phenomena, the short timescale phenomena, has greatly to be improved. The wish list in Geodesy is that we would like to have higher spatial resolution, that we would like to have higher temporal resolution, and most of all, that we have a continuity of satellite missions. I think with GOCE we have done a nice first step in terms of spatial resolution, and I think gravitational gradiometry is also very well suited for planetary missions like Mars or Venus. Also on the continuity, we have now made a major step due to the improvement of a follow-on mission. And this follow-on mission will at least be equipped with an experimental laser link. The temporal resolution could probably be improved if we would have not 2 satellites, but many more. And Peter Benner did some studies, and Steve Nerem did some studies. NASA and ESA have established now a joint working group that will look in future concepts. And I would advise that one also looks into less expensive concepts, probably with a cloud of satellites linked, among others. And we should also look in what the role could be of optical clocks for space gravimetry, for satellite gravimetry, of quantum gravimetry, and of quantum gradiometry. I come back to William Bowie. I have found this citation, and it's an advice on the younger generation and I have to underline it was a joke. So what he said, if you want to make a name for yourself in science, choose for investigation some subject which nobody knows anything about and which, moreover, nobody cares anything about, such as isostasy. Unfortunately, I have no time left to talk about our work with GOCE on isostasy. Let me finish with acknowledging contributions from my colleagues in Munich, from Jan-Martin Brockmann in Bonn, from Phil Woodworth in Liverpool, and from all my colleagues at the European Space Agency, at industry, and from our Level 2 processing facility for GOCE. Thank you very much for your attention.
Thank you for that really wonderful talk. I enjoyed that immensely. Are there any questions for Reinhard?
I hope not.
Oh, there should be.
Gene.
Gene. Yes. I wonder if we can get a microphone out there. Why don't you come up and use the microphone?
I really enjoyed looking at the visual of looking at the accuracy triangle of GOCE and GRACE. They really complement each other, and I thought that was magnificent to bring that up.
Thank you, Gene.
Well, I have a question. You note the physics problem of upward continuation and the inability to see something smaller than the altitude of the spacecraft. And what about aircraft gravity? What's the future of that? Is that ever going to reach this kind of accuracy?
Our colleagues from ONARA are here, and I think they're even in the audience. And ONARA in Paris is currently developing an airborne gradiometer. This is quite difficult and challenging because of the dynamics of the aircraft. But I think we absolutely need this link between satellite methods and terrestrial methods. And this gap can only be filled by airborne gravimetry, which is already successful, and hopefully airborne gradiometry too.
Are there any more questions? I can't really see the audience, so you'll have to raise your hand high if you have a question. Well, if there are no more questions, I'd like to give Rainer this certificate for his really fabulous talk that I enjoyed, certainly, and I hope everyone else enjoyed. And thank you again, Reinhard.
Thank you. Thank you.